Think math.
A radioactive element shrinks as time passes, but something is odd about how it shrinks. The time it takes for 100 grams to become 50 is exactly the same as the time for that remaining 50 to become 25. The amount dropped sharply, so why did the clock not change? The key is in how it shrinks. Each atom decays on its own, with the same chance, paying no attention to the others. So the number that vanish in a year is proportional to how much is left right now. Halve the amount and the number that vanish is halved too. The speed of shrinking falls along with the amount, so the fraction lost stays the same forever. Write that constant fraction as a formula, and you get an exponential. Call the starting amount A0, and call the time it takes to halve the half-life. Divide the elapsed time by the half-life, and you get the number of halvings. What remains is A0, with 1/2 multiplied in that many times. The graph shows it clearly. One step across and the height is halved. One more step and it halves again. It plunges at first and flattens out later, but the width it takes to halve is the same wherever you measure it. That constant width is what we call the half-life. Now read it backwards. If 1/8 of the original is left, how many halvings have happened? 1/8 is 1/2 multiplied in 3 times, so 3 halvings, which means 3 half-lives have passed. The tool that recovers that count, and so the time from the amount left is the logarithm. Radiocarbon dating in archaeology is exactly this calculation. To sum up, because the amount lost is proportional to the amount left, the fraction lost is always the same, and so the time to halve is always the same as well. However much you started with, however much is left now, the half-life is a constant belonging to that material. An exponential writes the shrinking down, and a logarithm recovers the time. A sip of math every day, here at Think Math.